Hello, calculus class. Sorry I can't be in school today with you guys. I have a meeting to go to. I'll try to walk you through our new lesson today as best I can through this video. For your homework that was due today, I'll be checking it when I get back on Tuesday. And if you have any questions on it, we can go over them at that time. Today we're going to be looking at the power rule, which we'll go into in detail in a couple of slides. But first, a quick refresher. What is the answer to the first question on your first derivatives quiz going to be? This is a thing we put in a box probably 5 or 6 times last class, and just to remind you, it is going to be that the derivative of f of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And another reminder, what does the derivative actually let us do? Well, the derivative lets us find the slope of a curve at any point on that curve. With that refresher out of the way, that brings us to our new method for today. Now, first of all, why do we want another method? Well, as you might have noticed, taking the derivative using the limit process can take a while, and there is a lot of places where a small mistake can throw you off pretty badly. And on top of that, the functions we were working with weren't all that complicated or all that big. As functions get bigger and bigger, like this function we have here, the limit method for finding the derivative would take forever, and it would be quite challenging to get through it without making a single arithmetic mistake. But by the end of class, with our new method, the power rule, you'll be able to find the derivative of a function like this in almost no time. Which brings us to the power rule itself, your very first derivative shortcut. The power rule says that given a function f of x is equal to x to the n, the derivative of that function is just going to be n times x to the n minus 1. Now, what exactly does that mean? Well, that means if we have a function that we can write as x to the n, we can find the derivative of that function by taking the exponent down in front of the x and lowering the power of the exponent by 1. We'll look at a couple of examples. So here we want to find the derivative of each of these functions. If we look at example 1, we have x squared. Now, applying the power rule, we know that to find the derivative of this function, f prime of x, we want to take our exponent and bring that out in front. So first of all, we know this is going to have a 2 out in front. Just don't have that x there, but we want to know, well, what is the new power of x going to be? Well, it's just going to be 2 minus 1, which is going to give us 1. So we can also write this just as 2x. So the derivative of f of x in this case is just 2x. We can use the same process even if there is a coefficient in front of our x term. For example, here we have 5x cubed. It doesn't matter that the 5's there, we'll just have to take it into account as we work. So if I want to find f prime of x again, I'm going to bring my 3, my exponent, out in front. So we're going to have 3 times 5, still have that x there, and we're going to take the 3 and lower the power of our exponent by 1. So 3 minus 1 will give us 2. Right, so our exponent came out front. We can't ignore the 5, so it's still there. And then x cubed became x squared. Now we can simplify this a little bit. So 3 times 5 gives us 15 out front. So our final answer here will be 15x squared. This also works for finding the derivative for constant terms. So I can rewrite f of x as 14 times x to the 0th power. Now, x to the 0th, if we bring that 0 out front, will give us f prime of x is equal to 0 times 14 times, if I lower the exponent on x to the 0 by 1, I'll have x to the negative 1. But none of that actually matters because we have this 0 out in front. 0 times anything is just going to give us 0. So our final derivative here is just going to be 0. Which makes sense because we know the slope of a horizontal line is 0 at any point. Moving on, we can also apply this when it's not just one term. We can apply this to things like polynomials. We have to take the polynomial one term at a time and do the derivative of each term. So if I look at this, I can find f prime of x by starting with my first term. I'm going to bring the 2 out in front. So that'll be 2 times 2, which means this will give me 4x to the first, which is just 4x. Here I have x to the first, and bring that 1 out front, which means that will just be 1 times 4, which is 4. X to the first will go to x to the 0th, and anything raised to the 0th power is just 1, so this will just be 4 times 1, or 4. And like we saw in example 3, a constant term can be written as that constant times x to the 0, and that constant term will always just go to 0. So our answer here is going to be 4x plus 4. Slightly more complicated on this slide. Before we can go too far with any of these, we have to make sure that our original function is written in x to the n terms. So right now we don't have that. We have 1 over x cubed. But I can think about 1 over x cubed as 1 times x to the negative 3. And x cubed is the same as x to the negative 3rd power. Now, to move on from there, I take the derivative using my power rule. I'm going to bring that negative 3 out in front of my x. So f prime of x is going to give me negative 3 times x. We have to be careful here. If I lower the exponent by 1, negative 3 minus 1, it's going to give me negative 4. So in this case, our final answer would be negative 3 times x to the negative 4th, or to follow our simplification rules with no negative exponents, negative 3 over x to the 4th. Moving on to example 6. Again, we have to rewrite our original function here in terms of x to the n. So the square root of x, if we remember, is the same as x to the 1/2. From here, we can apply our power rule. Our 1/2 will come out in front. So f prime of x will be the same as 1/2 times x to the, well, 1/2 minus 1 is going to give me negative 1/2. So again, to follow our rule of not having any negative exponents, I'm going to rewrite this as 1 over 2 times x to the 1/2, which I could further rewrite as just 1 over 2 times the square root of x, because x to the 1/2 is the same as the square root of x. Moving on to example 7. This one's going to take a couple of steps to rewrite our original function. This will become 3 over, well, the square root of x is the same as x to the 1/2. And then we can again rewrite that as 3 times x to the negative 1/2. We're just bringing that exponent, that term with an exponent in the denominator up to the numerator and making the exponent negative. So applying our power rule, we're going to bring the negative 1/2 out front. Negative 1/2 times 3 is going to give us negative 3/2. And then x, well, negative 1/2 minus 1, or we have to lower our exponent by 1, is going to now give us x to the negative 3/2. So we can keep going here. This will be the same as negative 3 over 2x to the positive 3/2, which we could further rewrite as -3 over 2 times the square root of x cubed, applying our exponent rules. Both of these would be acceptable final answers, though. We're almost to our last example. In this case, we have some weird exponents going on. We have 3x to the 7/8. So I can apply the power rule immediately here for this part. 3 times, I'm bringing that 7/8 out front, 3 times 7/8 is going to give me 21/8 times x to the, well, 7/8 minus 1 is going to be the same as 7/8 minus 8/8, which is going to give us -1/8. Now, the cube, moving on to our next term, the cube root of x is the same as x to the 1/3, so we'll have to bring that x to the 1/3 out front. Sorry, we'll have to bring that 1/3 out front. This will give us 1/3 x to the 1/3 minus 1 is going to be -2/3. At this point, we should rewrite our answer. So f prime of x is going to be equal to 21 over 8 times x to the 1/8 plus 1 over 3 times x to the 2/3. We're just rewriting our terms without negative exponents. There is one last case I want to look at, and that is when there's a little more simplifying to go along before we can start to find the derivative, other than just kind of rewriting in x to the n terms. In this case, we're actually going to want to split this up into 2 separate terms before we try to take the derivative, which means we're going to have to divide each of the terms in our numerator by this x. We're going to split this up into 2 fractions. So our first fraction is going to be x squared over x, and our second fraction is going to be 3 over x. Now x squared over x we can simplify to just x, and 3 over x we're going to want to write in x to the n terms. That will be 3x to the -1. Now we can go ahead and find our derivative here. So, applying the power rule again, x to the first, that 1 is going to come out front, times x to the 0, so x to the first just becomes 1. 3x to the -1, we're going to bring the -1 out in front, so -1 times 3 is going to give us -3, x to the -1 minus 1, which is -2. We can simplify this a little bit. We'll have 1 minus 3 over x squared. If you wanted to, you could even go a step further to turn this into one term. We could treat this 1 as 1 over 1 and get a common denominator, which would end up giving us x squared minus 3 over x squared. That's our last example for this. Your assignment for the rest of class and for homework is out of your book. It is page 136, numbers 3 through 17 odd, numbers 41 through 48, and numbers 57 and 58. On 57 and 58, you're only going to do part A. These are more problems where you're going to have to find the tangent line. I hope I was able to explain most of this. If we have questions, I can address them when I get back next class.